Congratulations, we have finally reached unit 10 that it's the last unit of the subject of the course and deals with environmental biotechnology. In this environmental biotechnology that I suggest you, if you want further information, there's a book available in the library and in internet, which title is actually environmental biotechnology, and it dips into the main concepts of the environmental biotech, which has three main aims. One, it's related with pollution, and it's about controlling and preventing. The second one, it's about waste and how can we manage this waste and how can we minimize it. And the third one, it's about manufacturing processes in the line to make eco-friendly products which employ less raw material and generates less pollution. This goes with the line of creating alternative energy sources. So in this environmental biotechnology that not only includes microbes but also plants and animals that can be used, the microbes play a key role due to their high diverse metabolic activity, their versatility to different environments, and they have a major role in as catalysts of matter and energy. Among the roles that these microbes can develop, we can have, for example, bioremediation. We can also have biocontrol. In bioremediation, we will see that deals with how the microbes clean up a contaminated environment. In biocontrol, we will see that they can generate antimicrobial metabolites and then reduce diseases and pathogens. We also have a role of an application of microbes in biofertilization, because many of them can fix nitrogen and can solubilize phosphates, for example, and that means that you don't rely on chemical fertilizers, so there's a reduce of its usage, and also water is less polluted because these chemical these chemical fertilizers normally contaminate a lot. Another application of the microbes we will see in the microorganisms in agriculture, that it's as a phytostimulation. Actually, stimulation. Actually, these three main applications are the ones that we will see in microbes in agriculture, in macro agrotechnology. Another role that we will also study in this unit briefly, it's as biosensors. When combined with a transducer, they can generate a response about, for example, the presence of explosives or detection of certain compounds. And they have a role, especially in they can be applied in all these areas because they can immobilize certain compounds, for example, heavy metals. They can transform them, and they can also mineralize them. They can change their chemical status, making them unsoluble and therefore removing from the environment. And these microbes normally work in consortia. That means that different communities and different species of microbes will work together, and this is based on the on a metabolic basis, and in the scenario of a microbial ecology, where the products of one community, of one population, serves as sources, as raw material for another population. So there's a biomass balance and biomass retention of all the carbon and the energy in the system. These biological processes play a major role in the removal of contaminants and take advantage of the let's put it like that, catabolic versatility of these microbes to degrade and convert certain compounds that work as pollutants. So in their role will be as catalysts of organic matter, because they can do these things, degrade and convert. One of the and their action, this and this, is going to be highly determined by factors that in the environment that can be abiotic and biotic. Both these factors are going to be the ones that will determine the metabolic activity and the efficiency of the role of the microbes in the process that they are involved. So favoring certain factors and the conditions to make these microbes grow, it's a basis to be able to use them in these applications, especially in bioremediation. One of the main applications of microbes in an environmental biotech context is the wastewater treatment plants. Okay, in wastewater treatment plants, there are different bioreactors employed, different settings, and different degrees of how to clean that water. This will be determined by the different types of water. It's not the same that you have an industrial water that might contain toxic chemical substances rather than an urban sewage, which mainly contains organic matter. Okay, so in general, despite these variations among the protocols, the workflow of wastewater treatment plants is the following. At first, there's a preliminary treatment, which can be chemical and physical, where the big blocks, big solid materials are removed. Then, so here we will have some sludge. Then this is submitted to a primary treatment. And this primary treatment, it's mainly physical procedures, mainly as filters and decanters or sedimenters. Okay, where solids can precipitate and they can be collected in the sludge. Afterwards, we have a secondary treatment. And this secondary treatment is biological. It's where our microbes take place. Okay? Here, it's also generated as sludge. Okay, and we will comment a bit more about the biological treatment in a moment. And then this goes to a tertiary treatment. This tertiary treatment sometimes is not done, or sometimes the secondary treatment is supplemented with a clarification or another kind of technique instead of doing a tertiary treatment. When we're going to step only in secondary treatment? When, for example, the wastewater treatment plant is local, or it's it has low amount of water to treat. It's more more small, and therefore normally and employs urban water, and normally they don't need a higher treatment. This tertiary treatment can be biochemical, and it's mainly with oxidations and desalinizations. Okay, and after this tertiary treatment, the water should be nice and of good quality. Okay, this is normally achieved by biofilters when it's biological. Okay, we said that, and here also we can get some sludge. What happens with the biological and these sludges? All these sludges and the biological part, it's normally done, or it's normally eliminated or degraded or treated in bioreactors. Okay? And these bioreactors normally can be of two types. Okay? We can have the membrane bioreactor, and we can have the trickling filters. This is the most common ones. Okay, how does this membrane bioreactors work? You have it's like a combined system, okay, where you have an agitated tank, where you have mainly with bubbles, with some sparklers, where you favor the mix of the wastewater, and here there's membrane filtration. Okay, and here you have the membranes, okay, with the biocatalyst immobilized and some filters where the final degradation it's done. This is also coupled with microfiltration, okay, and here is normally where your main biocatalysts are. Here you can have only the filters, but also sometimes they can be amended with certain enzymes and certain microbes in order to promote the bioactivity inside the bioreactor. What's the type of the trickling filters? These are normally more rural and more basic, and it's mainly like if it was an umbrella, okay? And it's like when you go to the fields and you see how they big devices that set the water in the big fields for the crops, they have here some sparklers, okay, from where the wastewater it's expelled. This wastewater reaches a porous matrix that is called a slime layer, okay, where your biocatalysts are. Okay, here the biocatalysts will get into contact with the organic matter in the sewage, in the wastewater, and will catalyze the reactions. So what finally is collected here, it's clean water that can be further on treated in tertiary treatment or cleaned by another system. In biological treatments, in these bioreactors, we normally employ consortia of these microbes. Okay, these consortia of these microbes work in the principle of this biomass retention, because some of them will, for example, produce some acids that will serve as raw material for another kind of microbes that will consume these acids and these components. Which kind of microbes do we find? Normally, filamentous nitrifiers and denitrifiers. We can have carbon oxidizers. We can have different kinds of microbes. normally immobilized because it's more efficient, the process, okay? And normally also taking advantage of the properties to make biofilms and floccules, which can make aggregates of the sludge of the waste of present in the water, which is easily or is removed afterwards more easy than if it's in a soluble state. This kind of treatments and this consortia will combine aerobic and anaerobic microbes, because different processes will require or prevent the presence of oxygen. And this is more or less the basis of the bioreactors employed. How do we estimate the biological efficiency of these wastewater treatment plants? With certain monitoring parameters. Mainly, we will check about the biomass, and this biomass is mainly measured by BOD and COD. These two parameters that are kind of different, both determine biomass, but COD gives you it works quicker. Okay, so normally you will rely on the COD measure. You can also measure solids with total solids like that, or the amount of carbon, okay, or dissolved oxygen. And by these parameters you can estimate the activity, the biological activity that is being held in the bioreactors, and